Thanks. So I want to talk about why we're here a little bit. We were super inspired by some of the work Microsoft and other people have done in creating DEP and ASLR. When I was getting out of college, the presence of DEP and ASLR kind of affected my career. I was thinking like, oh boy, like, memory corruption is like a solved space now. So I better go into application security. And I wasn't exactly right, but the vulnerabilities we see at Pwn to Own, like 7 things chained together. Every exploit there is a piece of art. So that I think we were inspired by it. We wanted to see what we could do at the app layer to complement. So we both work at Contrast Security, and let's get started. So we hate this slide, but we're company men, so we let marketing put it in there, and we're going to zoom right past it. The first leg of my argument that I'm going to try to make today is that tailored security never scales, never succeeds in the long term. So what we see going on in the background here is an example of a Java security policy. So if you wanted to tightly sandbox, tightly control what your system is allowed to do, you can do that. They give you tons of complicated configuration, and there's interesting academic papers about how best to use tools to infer what your policy should be. And over time, these things lose momentum, and development teams end up throwing them away. I'm sure the red team and blue team side of all of your teams have seen that this is not deployed in production. Right? This is used in the browser sandbox for Java applets and really practically nowhere else. A more modern example is content security policy. I think, I'm not ready to say it's dead or anything, but I think adoption outside of the traditional unicorns is low. And in fact, some of the trends are in the wrong direction. So we see here people when they're including a script source directive, where can scripts come from? They're actually tending to more often choose an allow all policy, like any origin can provide scripts, because this is an extremely hard thing to maintain, right? It's difficult to get right in the first place. It's difficult to maintain as you grow your team, as you're changing your partners, adding rum, doing whatever. It just gets hard. So I don't think that works. SE Linux is another example. There's some key use cases that really it works well. It ships with some of the Linux distros. It's on Android, I believe. But it's if you want to deploy this for your system for your particular use case, it's a lot of work to get started. You need to be an expert at rule writing, even to look at the results. So the second picture here is a picture of the results of an audit event, and you'd have to be super expert just to understand what is in there. I don't understand what's in there. So probably the most relevant example for the rest of our talk today is about the WAF, right? The Web Application Firewall. So it's complicated in terms of the rules you have to make for it. Requires constant tuning. You can see here there's a clip from an actual Web Application Firewall datasheet where they advertise like, "Hey, comes with our product, this service of people to maintain rules for your app over time because it's something that really needs a lot of hand-holding forever." And so the web application market, I think right now is around $1 billion, and here I am saying it's not working, but people don't really have an alternative. So the second leg of my argument is about perspective and context. Like, I strongly believe that security gets a lot better closer to boom, right? Closer to where exploitation occurs. And I think history has shown that what we've done is we've taken security mechanisms and move them closer and closer to where the time of boom, the time of exploitation, and we've gotten much better gains from that. And it's a little bit counterintuitive because, are you suggesting to me that I should let the attacker get closer in and then we should try to stop them? But I think we've all kind of recognized as a community that the moat doesn't work, and the best context is at the exploit. So let's not run away from that, right? Let's run towards it. So I've been super negative so far. Sorry about that. But let's talk about what really works. And I am super fanboy of DEP and ASLR. And the intent of these mechanisms is to inject security capabilities using the compiler, using the OS, to to kill whole bug classes that the developer doesn't even have to know about, right? So we're a huge fan of these techniques that either kill bug classes, raise the cost of exploit development a lot, and they're done invisibly. So when I look at the security spend inside of our customers, inside of the market, I get a little frustrated because here's these things that we can focus on, like DEP and ASLR and all this stuff, that they're big upfront costs. They're a little bit, it's a little bit tough on the world to get them out there and well deployed. But once they're done, I mean, the returns are huge. I would say there's nothing that changed the security needle, nothing that moved the security needle like DEP and ASLR and sister protections like it. All the secure coding guidelines in the world, all the things that we do in application security, the presence of secure APIs, we had all those things for a long time before we had DEP. But you had to get people to use it. You had to hope that they understood how to use it correctly. You had to hope that they retained the muscle memory to know when they should use it and when not, and all that kind of stuff. And all of the activities that we use in application security are all expert activities, right? They all need an expert, and there's just not enough experts to go around. We need developers to be able to self-service on security. So it super frustrates me that we spend a lot of our time and money on this. So we need stuff more like the right. So we want to talk about how the research we did to affect that change, to try to translate some of those protections. Obviously, there's no stack. Well, there is, but there's not the same constructs of memory corruption in the application layer, but how we try to capture those intents at the application layer. So the first thing is, how can you change an application to automatically infuse new security capabilities into it? And the way you do that is through instrumentation, right? So typically you provide an agent that can monkey patch or source rewrite or redefine the types of the code so that you can change the behavior, get more sensors in there. So in this example, we're showing that how once you add an agent to the runtime, it can modify any of the code, whether it comes from libraries, frameworks, et cetera. And these are now interesting security sensors that we have all throughout the system. And so what we're trying to get across today is not a particular product, not a particular really anything except for the fact that we are trying to communicate that there is a framework that we coined here called runtime exploit prevention that is a strategy for infusing security protections into a running application. So as a workload progresses, like an HTTP request is executing, we'll have several opportunities to infuse proactive controls, to harden, to sandbox, to detect injection attempts, to do all kinds of things. So being within the running application gives us all these places where we can do security that we didn't have before, right? If we think about our only competitor here as a web application firewall, the only thing we can do is reject it up front. It's really an impossible ask of that tool. It's a network tool trying to do an application layer job, so it's really unfair for us to give it the job that it's doing. But now we have all these other stages through this framework where we can say, okay, well, how can we use hardening to prevent XXE attacks? So we can do hardening and sandboxing. We can also, if we detect that, if we think we've built up sufficient evidence that an attack is going on, we can also block it, right? We can throw an exception or redirect the control flow so that the application doesn't do the exploit behavior. So we're going to go through each of these stages of protection, and Matt's going to start us off.
Hey, so when we can do input classification, we can classify upfront or look at the input and decide that something is malicious. So there's some obvious input vectors. So there's some things that just don't make sense and can seem like malicious behavior. So this is definitely invalid. It's negative content type. There's a super long content type. There's a more recent struts vulnerability, and that was an injection through the content type, and any reasonable payload was thousands of characters, and so just that alone is enough to say that this doesn't look right. This is not a standard content type, and it also has, it's way too long. It's bigger than anything else you see coming along. And like I said, like something looks super obvious up front, you can still stop it at the gate. You don't have to let an obvious attack get really far. Then there's things you can do with volumetric analysis. So like a regular expression DOS, we can handle that by watching the number of actions inside the application. We can count during that request cycle how many operations happen inside a single request to know that this regex is doing something extreme and being potentially malicious. And the other example is a padding oracle. So a padding oracle, if you throw an exception based on padding, you can eventually leak the key. But you may also have errors that are truly about padding, or the user corrupts the data unintentionally somehow. And so we can actually hook into this exception handler with the agent, and then we can keep track by an individual, by some analysis of who the current user is, and start tallying up those exceptions, and then eventually block an attacker or detect an attack based on what in a single shot would be normal behavior, but now is defined as an attack. And by accumulating these events, we can identify it as an attack.
It's only from being within the application that we can observe this padding exception, right? Trying to detect a padding oracle attack with a web application firewall is extremely difficult, right? You have to somehow build some state about each payload and try to detect, are they trying to iterate on it, and how far are they getting? But being within the application where the vulnerability is exploited, I mean, there's really, we haven't done that yet, right? So.
And so there's this other idea of input tracing, and it's more or less following input through the execution of the application. And when you see that input, when you see something that came from input in a malicious trigger, you do some analyzing and see if it is indeed malicious. So we can take a look at a standard SQL injection vulnerability. And we can see the request comes in, the query's built, string built from a request parameter, pretty standard, and then we execute the query. The goal is to block this request because it's malicious. And so at the execution, at the command execute, we can look at the query itself and parse the query. When we parse the query, we can break it up into tokens and actually analyze the input. And now we can say, we saw that test example or 1 = 1 come in through the request. We see it in this SQL query, and it broke the boundary. There are token boundaries that we crossed. So the user input changed the outcome of this query. It wasn't used to just fill in that text box. It actually changed with the intent of the query, so it's malicious. And that context you can only get by understanding what the query was going to do. So yeah, user input comes in, we hit the sync command, and now we can analyze and block at the correct point.
So it's like the purpose of DEP is to prevent the attacker's cargo code from executing on the stack or the heap or whatever kind of writable space. And so really what we just described, detecting input, changing the structure of the query, we capture that same intent, right? It's not the same primitives, but we were able to stop the attacker's code from running because we detected they were about to change the structure of the query. But sometimes you might not see so what Matt just described, this one strategy, input tracing, depends on being able to see the input come in and then reaching this call. But what if you don't see that call for some reason? What if it's an asynchronous app like a lot of apps are today, and the attacker sends the bomb to something like an S3 bucket, and then some other app somewhere along the way pulls from that bucket, and that's where the interpreter or the SQL execution happens, and that's where the bomb explodes. In that case, the interpreter doesn't have the context of where the bomb came from, so they can't trace it to any input. But we can still give ourselves an opportunity to catch and diffuse this attack just by doing some semantic analysis. So here we have a similar query that looks like it's been injected into to do, a lot of SQL injection examples are about or 1 = 1, right? They want to evaluate true to every row. So that 1 equals 1 part is called a tautology. And so this is a little bit more advanced as these things can be, a tautology. So this is 1 not equals to the square root of 4. So the square root of 4 is 2, so they shouldn't be equal. So this is an obviously purposeful tautology. So they're trying to get it to a value to true for every row. So we can detect that this appears to be a malicious clause without trying to tie it to any context, right? We don't necessarily know that this came from an attack, but if this is a behavior that isn't typical for your systems, this can be weaved into your application. And of course, the running theme here is all of this is provided by an instrumentation agent. It's not provided by a developer. Developer's not writing any rules. There's no tuning. This is just something you get for free by adding our agent.
And again, the 1 equals 1 can be detected, but that square root, we need to, we have pseudo-evaluation, I guess, like the callout says. So we can kind of evaluate that and determine that 1 doesn't equal the square root of 4, and we evaluate that thing. So we know that it truly is a tautology and not some string-built script that was unintentional.
That's an excellent point. Yeah, we have the example here that, if you were to try to detect this statically, just scan the code and check if the expression on the left is the expression on the right, it'd be trivially easy to bypass that through string concatenation or whatever. But if you evaluate, I think FireEye is well known for kind of detonating, binaries that might be malicious and seeing how they behave. We can detonate the query, right? We can run the query through a fake, simulated runner and see how it behaves. And if the expression on the right, resolves to some constant value, no matter the input, and the expression on the left also resolves to that same value, then we detect this tautology. So this is another example of detecting something unusual, which is unioning with system tables, right? So if we detect that you're unioning with system tables, most applications don't work like that. If your application does something weird, like when DEP was coming out, people were complaining because GCC needed an executable stack because it had some trampoline code or whatever. Like, fine, if you want to do some really weird stuff, you can do that. You can turn this off, whatever. But most applications, 99 applications out of 100, aren't going to ever union with a system table. That's something strictly for exploit writers. And then chaining, too. Chaining is a really simple thing to detect semantically just by parsing the query. So most people, again, don't chain. And they certainly don't select and then drop constantly. So this is, so we get warnings when we try to compile C code that has the gets function because it's trivially exploitable. And so if you want to have behavior like this, fine, we'll give you a warning. But most people don't need it. We should harden it. We've been talking a lot about SQL injection. We just wanted to have one slide that wasn't. So the strategy applies to any interpreter, right? LDAP, SQL, any, the browser, et cetera. We can see in this example, we can detect the expansion. We kind of simulate execution of it and see if it's going to do something malicious with semantic analysis. So we can also harden. What we've been trying to talk about so far is all those first stages have been about let's detect attacks, but we can also harden instead. So the first thing we thought of is like, okay, what if we could do ASLR in the application layer? So I'm a Java guy, so I went through this process myself. I went to the runtime and I tried to hide the runtime class. The runtime is how you execute system commands. So we hid it under some namespace, and we said, okay, does this work? If all the regular code can access it, but somebody's new code, if somebody gets some malicious code in there and they tried to get access to it, would they be able to? And it turns out this was really not a super fruitful exercise for us. Like, we thought it would be a cool protection. It ended up not being that useful. So if the exploit previously pointed to Java-lang runtime, well, if it's in an unpredictable location, that's going to be tricky, right? But actually, it turned out to be relatively easy. The exploit code, instead of having a direct link to runtime, sure, it couldn't find that because it's not there anymore. But there's a lot of other types in the system that have hard links to runtime. So no matter where runtime moved, I may not know its direct location, but I'll be able to find it by going off another type that has a hard link to it. So that's one way we were able to bypass this technique. And then another way was to build another signature of that type. So sure, we didn't know what the type name was. This runtime, hidden runtime, it's out there in the JVM under a different name. So we came up with some other signature of it. And then we looped through all the types available in the system, and we said, okay, who has 1 integer and 3 strings in their class definition, and they have this serialized version ID. Okay, so if we can find a class that matches that signature, then we know that's probably runtime. And if it's not, then we'll go on to the next one. And there's only a limited number of types, so it wouldn't be difficult at all to spray through the 20 to 100,000 classes that are in the virtual machine and find the one you're looking for. So we're basically a big to-do about nothing, right? We thought it would be this cool experiment, and it actually ended up going nowhere. But let's talk about something that was successful. So this is a piece of vulnerable code. It's vulnerable to XML external entities, which can be used to exfiltrate data, access internal resources, etc. So this is the vulnerable code. We get access to an untrusted HTTP request, and then we parse the XML that comes out of it. So it's trivial for an instrumentation agent to weave into that to disable access to external entities. Nobody uses external entities legitimately. Like, the first 75 links you get when you search for external entities are all about attacks, of course, because it's just not a generally useful feature for XML for normal use. So you can't get any closer to boom here, right? We're literally injecting our protection 2 lines away from where the exploit happens, and you have full context. You know what's about to happen. You know the input is untrusted, and so it's just a much more surefire way of protecting your system against attack. So I just want to talk about sandboxing. So we know that there's, people find bypasses for the sandboxes, in the browser, very popular, but they do raise the cost of exploit development a lot. So it's generally really positive. If we can do the same thing, we want to do it at the application layer. So there's been a lot of publication about the vulnerabilities in struts, which is a popular web application framework. And so we said, okay, all these vulnerabilities are based on expression language injection. The expression language is called OGNL. And so we said, okay, all of these exploits that we see in the wild that were, very rapidly coming out from, within 24 hours of the Git commit that patched it and the vulnerability announcement, we're seeing attacks from all over the world. Most of them were using that same runtime type. They were just executing system commands. And so we can see an example of that. Here, the attackers are running the ID command. This is just a simple proof of concept. So we want to be able to prevent OGNL from accessing runtime. So let's sandbox it. So what we see here is the OGNL evaluate. This is the stack trace of that exploit actually occurring, right? So this is the runtime exec command is occurring. So the system command is about to be run. But what we can actually do is we can say, okay, when we enter OGNL evaluation, when we're about to evaluate some input that could be untrusted, we'll enter a sandbox, right? We'll set some global state that says, hey, we're about to do this dangerous operation. And then if we ever go into runtime, we can check to see if that state was ever set, right? We can check to see, did we go into the sandbox? If we did go into the sandbox, we're about to fire off a system command while we're inside OGNL evaluation. This is no good. We should block this, right? We should throw an exception or otherwise redirect control flow. So I want to go back to our framework here for just a second and try to explain why I back this strategy so much. Is because if you have a web application firewall, you have one opportunity to catch this attack, right? It's when the application hits the perimeter, you have to make a decision then, like, did my signatures match up to the attack that's given? If yes, then block it. If not, the attack is going to succeed. But we gave ourselves 3 ways to catch this attack. And it comes from having these different strategies, having these different protection capabilities. So if we see obvious OGNL attacks, which some are easily detectable, if we see that in the input to the perimeter, we'll just block it. Like, go away. This is obvious. If we see input that might be OGNL, like looks like it's suspicious, but maybe it's difficult to classify, well, we'll check to see if that input ever made it into the OGNL evaluation, right? So if we see something suspicious, we don't have to make the decision right away, right? We can wait till we have better context, and then once the evaluation happens, we can say, okay, well, this malicious expression came over here. Now it's being evaluated as code. I don't care what the attacker gave me. If it's going to run as code, I don't want to run it. And then even if the attacker gets by both of those things, we can actually sandbox them, right? We can prevent them to getting to the common exploitation paths. That's what I just walked through, trying to prevent runtime from running within the OGNL evaluation. So giving ourselves 3 options, 3 strategies for blocking it is really, really powerful. So goals of rep for us, we want to kill bug classes, right? We don't want developers to have to know or understand about XXZ or SQL injection, padding, Oracle. These are complicated subjects that require real muscle memory around security, and asking developers to keep up with it, for me, is boiling the ocean. When New Relic and AppDynamics introduced agents to measure security, they didn't try to go out and teach the world how to write more performance managing measurement code. They just said, we'll handle it. We'll handle the performance stuff. You just write your business logic, right? And we want to do the same thing. We want to add the missing security features through an instrumentation agent. So we want to kill bug classes. We want to be invisible to end users. The first question I think a lot of people would ask about using an agent to do this would be, what's the performance impact? And this is a funny question for me because if you think about SSL, in a classic picture, SSL is terminated up front, then it gets handed off to the web and then the app server. It's probably adding, let's say, 5-6 milliseconds or something. Well, SSL provides an important set of protections, but it's a small set. Whereas, all the protections that you could do from within the runtime, we're talking about the cost of CPU cycles, right? It's obviously a much lower cost, and we're preventing entire, much bigger sets of vulnerability classes. And then we want to be invisible to developers too. So I hope we were able to prove that today as well. So developers don't need to write complex policies. They don't need to understand a lot of these complicated security mechanisms, and provide them with the security that they need. So to compare DEP and sister protections like ASLR, DEP is really about protecting these meta programming points, right? The structure of the application as it's running in memory, right? It's trying to prevent memory corruption. It's trying to prevent the attackers, from controlling where execution flows. But they're trying to stop one interpreter from being corrupted, right? They want to stop the CPU metal from executing one piece of code, right, from the attacker's code. Whereas at the application layer, it's a little bit more scattered, right? There's several different types of attacks. There's several different types of interpreters. So there's a lot more primitives. There's a lot more interpreters for you to talk to and try to protect against. But in many ways, they're similar, right? We're trying to prevent attackers' cargo code from running. We're trying to make sure that they can't follow the common exploit paths. And we want to be invisible. We want to be as part of the tooling, right? So we think we're not here to hawk a particular product or whatever. We just think the strategy of being an agent using instrumentation is a lot more, provides a lot more complete picture of security than just a web application firewall up front. So how do we get there? If we all agreed, like, okay, let's go do this. Microsoft is, we're here at Microsoft. Let's talk about Microsoft. I think it's an interesting, they have an opportunity because they offer a really complete ecosystem for their developers. So they control a lot of the APIs that developers use to do request processing or SQL APIs or XML APIs. So they could actually do this protection from within their virtual machine, within the .NET CLR. But it's a little more complicated if you're a node, right? So if the node runtime wanted to do this, a little more complicated because Express comes from this open source package, and you have these other libraries that do these other big chunks of it. So as the runtime, it's a little bit more complicated for you to try to instrument these other ecosystem partners, and so it's a lot less clean. So I think it's got to be done by a third-party open source, commercial, whatever. So we've done the research, we've built prototypes, we've gone through. We have a free edition of this available out there on the web. You can go download it and run it. We have we support all the Java, .NET, Node, Python, Ruby, and so you can go get it for free. You can go download it right now and play with it and test it out. Anything to add, Matt?
Great. No.
Awesome. That's it. Thank you for your time.
Any questions? Or?
Question?
Hey, do you guys know of any other, say, open source projects or something like that that would give you some limited introspection abilities into common application stacks, or is that just something that you guys are doing?
In terms of security, I don't think so. But there's lots of open source agents that do really cool things. There's some performance management ones. There's one called Introspect that does exactly that. It monitors your stack, tries to really build a complete performance measurement of your application. You instrument this app, you instrument that app, and it builds you some nice visuals and stuff. But on the security side, I don't think so. I should say that this has been experimented with in runtimes like Perl had a taint mode, if I remember correctly. And it was a really simple binary taint. I mean, that was years ago. This is like 10, maybe more years ago, maybe longer, where, yeah, if you just had an input and that input ever reached, was ever string concatenated and it reached SQL, it would blow up. So I think it's been played with, but not really fully chased down.
Hi. One question about when you were talking about semantic analysis, it has to be executed in every request that is made, and compared to the existing one, the time impact might be quite high. When you explain the external entities and such, this makes hell a lot of sense. But in sense of semantic analysis, this is quite resource, needs a lot of computation time compared to others.
Yeah, we thought so too. And really, most of the queries that execute on a system are the same over and over and over again. And so it's possible to cache the results of that analysis. So, and if it ever changes and it's a new query, then you do want to spend that extra few cycles checking out that query and investing some time into it. But most of the time, because of caching, it ends up being pretty fast.
Typically, you're not doing full query evaluation. We're not building a full our own SQL interpreter. It's a lot of build the ask, compare the tree of the abstract tree, and make decisions or figure out what's going on. We don't necessarily have to have full evaluation of everything, but there are methods like.
Well, for the tautology, I think he's talking about, we had to resolve the expressions.
We do resolve some of the functions and stuff like that to get the results, but it's just converting those to literals to compare later. We still don't have to build a full SQL engine and run all the queries at runtime.
Yeah, it's surprisingly cheap after really investing in the performance, but it's a great question.
Okay, thanks.
Hi, great presentation, guys. Thank you. Just a quick question. You said you have for different type of requests, you have a sandbox. Can you elaborate that a bit, please?
So
are you using a real sandbox? For example, if you have a SQL query, will you actually go to the file system or go to the database and run it there? Or do you have something virtually, locally, or how?
So some of the sandboxing is done really by sandboxing APIs from reaching other APIs. So it depends on the vulnerability type. But if we just put some state that says, okay, we're within OGNL, and we shouldn't ever reach this other command executing code, when we run this code, we always check to see if we're within that code. So it's not a sandbox in the traditional sense where we're trying to restrict access to resources or files or some other construct. It's about limiting code from reaching other code. But hey, look, tomorrow if we want to add support for a new vulnerability, what we're going to do is we're going to put that framework on the board and we're going to say, hey, what can we do for input tracing for this? What can we do for semantic analysis for this? What can we do for sandboxing? And maybe we'll end up doing something like that, but
so basically you're
so
restricting classes of APIs from interacting or talking to each other or calling each other, right?
In a sandbox. But in your example of a SQL query that's reading a file and maybe you don't want to do that, I think that, we have triggers for after we parse a query for identifying that this is like reading a file resource. And then that's a feature you can say, my queries don't read files, so that's something I don't want. But that's more done through analysis of the query as opposed to the sandboxing approach, because that query happens on the SQL Server, or that file read would happen on the SQL Server.
Got it. Thank you.
Thank you.
It's harder, yeah. Once it leaves the scope of the virtual machine where the app runs, the app's not running anymore, so we can't see what that person's doing. But luckily, we can do a whole lot from the app perspective.
That was great. Thanks, guys.
Thanks, guys. Appreciate it.
Thank you.
I love this talk. For me, it represents a promise because as defenders, as developers, we have to get everything right. As attackers, they need the one thing right. And to me, this represents the promise of us having to get less things right and some cavalry coming to kind of save our butts when we miss a few things. So yeah, great talk. Thanks very much.
Thank you.
I think there's a big advantage, too, of being able to weave in protections that you didn't have. Like if there's a new exploit that comes out and it affects a library that you have, but the code review or the time to remediation is so high, we can still put protections in, or we can block the OGNL from executing or whatever that type is before you can get a patch in place and deployed. So you can be protected from a class of vulnerability from a type, without waiting for long-term exploitation and things like that. So,
Expressed negatively, I think it allows me to be a lazy developer.
That's exactly what we want. That's
and
all
to
we
just
want.
eat all that security tech debt that we heard in the keynote, talked about it being oppressive and depressive.
Well, it's interesting. I don't know. I don't write C++ code anymore, so I don't know how developers think about using bounded APIs anymore, like string copy, and I assume they want to do use those controls, the secure APIs, so they don't have crashes or anything. But I wonder if security is forefront anymore. Like a lot of that stuff's really hard to exploit now, so maybe it doesn't make sense to really have to think that hard about it.
Hope so. Thanks.
thank you.
Thanks.